First of all, thank you for coming. My name is Guillermo Valdes. I am a postdoctoral researcher at the University of Texas, the Texas A&M University. I'm working for the Aerospace Engineering Department, specifically for the Laboratory of Space Systems and Optomechanics. So we do several stuff related to, especially we create all these seismometers, but also we do detector characterization for LIGO. I will explain more or less what is this. So to begin with, just to give you a brief introduction of what are we going to cover in this presentation. Let me tell you that gravitational wave detectors are very sensitive instruments and can be overwhelmed with these glitches, what we call glitches. And we call glitches to sporadic noise, very short duration, that come from non-astrophysical sources. And it's essential to find the origin of these glitches in order to mitigate them. So we employ all these machine learning techniques to identify, in particular for this work, acoustic noise that it's produced by the instrument. But in this case, it's going to be about external sources and that produce glitches in gravitational wave detectors. And finally, or the second part of this presentation is going to be a summary of the feature extraction procedures that we employ, the unsupervised and supervised learning that we combine with parallel computing techniques to achieve this goal. Very important, this work it's possible thanks to the effort of all the members of the LIGO Virgo Kagra collaboration. That it would be impossible to for me to do this without the help of them, but especially to use all the resources that we have available. First thing that I'm going to talk to very quick, gravitational waves. What are these? Are ripples in the space-time. Just to remind you, just imagine a pond and you throw a stone, and the waves that you see something similar, but with the space-time and these huge events that we are able to, that produce gravitational waves big enough to be detected by the instruments that we have. And all these detectors are very sensitive. I'm calling detectors to each one of these. In a group, we call them observatory because we need at least two to locate the source of all these gravitational waves. So we have several across the globe, but I'm focusing on the LIGO, which is one of the most sensitive or the most sensitive nowadays. And this particular work is for the LIGO Livingston detector. So each one of these gravitational wave detectors consists of this laser going through a beam splitter, and then you have two arms. You have this interferometer that more or less it works to detect changes in distance. I'm giving you a very brief explanation, of course, right? Because this is more complicated than that. But you have the laser entering the beam splitter. You have two arms. In LIGO, the arms are 4 kilometers long. And then you have the recombination of these lasers, or I'm going to call them twin lasers. And when the gravitational wave passes through the gravitational wave detector, you have some back and forth, like one arm extends and the other one shrinks, and you go back and forth. And that's when the light, the lasers, recombine and make some kind of patterns that we can recognize, and that's how we detect the gravitational waves. But besides that, we have many systems that help to keep everything still, right? Isolate the detector from all these disturbances like ground motion, acoustic noise, and many others. So here we have a little bit more complicated diagram that has the mirrors and the laser. But what I want to show with these images is that it's not only the interferometer. We have several systems, but also thousands and thousands of sensors. And that's when we have, in this case, we have monitors for environmental disturbances. We have accelerometers, we have temperature sensors, we have also magnetometers, but for this talk, we're gonna focus more in the acoustic noise, which is the noise recorded by the microphones. So now we have thousands of sensors. We have basically, in summary, we have a lot of noise and a lot of data to analyze, right? And we need some kind of tool that it's automated to find the noise origin. Otherwise, it's going to take, just imagine all these thousands of sensors are recording 24/7. Most of all the days, for the whole year. Some of them have sampling rates of 16 samples per second. Some of them 16,000 samples per second. So it's a lot of data. And what we want is to improve the detector sensitivity, right? So by looking at the origin of this noise, we can mitigate, but also we can help to some tasks that we call validate the candidate events. That's when we have some events, we have some detection, and we call it candidate, and we want to validate it. So we want to support this task of seeing, is this a noise? Can we remove it before we do the parameter analysis, the estimation of the parameters of these gravitational wave sources? So that's the motivation of this work, right? What is acoustic noise? We call acoustic noise to all the noise recorded by the microphones. That's what we are calling right now, acoustic noise. Why did we choose this noise? It's because it's easier to recognize by humans. Let me explain this. Let's say we have all these sensors, and now we want to, without any machine, we want to recognize ground motion, right? It's going to be hard to replicate that. So what we do is to hear what the microphone recordings, and we just plug it into a speaker, and we can recognize that. So that's the main reason we decide to use acoustic noise, but we can do several other things. One important tool that we use is the Omicron. So for the data that we collect, we use what we call Omicron triggers. But what is Omicron? Omicron, it's a tool that was created a long time ago, and it's available in LIGO, one of the gravitational wave detectors. And in summary, what it does is to find segments of data that are distinct from the rest, right? If everything's quiet, whenever you hear a loud noise, that's what we call a trigger. And what we have for each one of these sensors, we have thousands of triggers in a day, right? So we just gonna focus on one. And this one is gonna be the microphone that is located in one of the arms of the interferometer. So just to double check this diagram, again, we have the laser entering the interferometer. We have the beam splitter. You have two arms, 4 kilometers each, and then it comes back, the laser recombines, and you have the output. And as you can see, we have several vacuum chambers enclosing all these mirrors, but we have all these what we call environmental sensors, fields and acoustic noise. So again, we are focusing on this microphone. I'm adding here a picture, and it's interesting because most of the time, not too many people go inside the detector. So we have several pictures, and this is one of the microphones. For example, let me give you an example of how these acoustic noises go into light. We have a lot of thunderstorms in Louisiana, right? Remember, just to go back to this one, we have one in Washington, the other one in Livingston, Louisiana. And Livingston, Louisiana, it's very close to Baton Rouge and New Orleans, and these two cities are in cities with the highest amount of thunderstorms per year in the country, right? So it's interesting to study the thunderstorms effect on the gravitational wave detector. So these thunderstorms are frequent. Then you have a thunderclap, and you have also the rumble, right, of the thunder when it strikes, and that elevates the ground motion. And There is one particular noise that it's called light scattering noise, and that's this one. It's created when you have, first of all, I'm gonna say it's common when we have or when we work with optical cavities. Why? Because you have the laser or any light, right? And then some fraction of light escapes this cavity, and if some reflective surface, and then some other fraction recombines, right, from that reflective surface, recombines into the original cavity. So now you have this light also resonating. If this reflective surface outside the cavity it's moving, you will have some noise in your cavity that is proportional to the motion of this cavity. So that's what we call scattering. In short, we call scattering in LIGO. You have this kind of noise when you have optical cavities. So going back to this diagram, the storms produce this elevated ground motion, which produce this motion into the reflective surfaces, which produce scattering, and that reduces the sensitivity of LIGO. So that's one of the reasons why it's important to take a look to all these noises, acoustic noises. Now let's see what all the acoustic noises that we have in LIGO. So again, we use the Omicron trigger for the LIGO Livingston Observatory in the X arm. We have many of these triggers per day, and actually this is the amount of triggers or recorded by LIGO or by Omicron during the third observation run. And we separate it by time and by day to see if there is some kind of pattern. And the pattern that we see here is that we have a lot of noise in Sundays and not too many in Tuesdays. And that's not very helpful. The thing is this, we are using what we call observing time. And observing time is when we are ready to detect gravitational waves. And we are more likely, as LIGO, LIGO is more likely to be locked during a quiet Sunday afternoon than during a Tuesday that it's dedicated for maintenance. So that's the reason we see this pattern, but it's not that we have more thunderstorms on Sundays or things like that. But what I'm showing here is that we have our data set, right? We have all these triggers collected. But now we want to investigate what are all these triggers, right? So this is the second part. So we have the first part that it's a feature extraction. We want to apply dimensionality reduction because, well, I'm going to talk more about in a bit, but we have several features that depending on that noise, we will have different values. We want to reduce this, and then we will do unsupervised learning, basically clustering, to find some groups and see what are those. And then we can use that information that we already collect for classification. And the classification will help to predict future noises or identify future. Very important. This work has been developed by students with me. I mean, I have received many help from graduate students, especially from the Texas A&M University, Brina Martinez, and collaboration, right? It was not only my work. So the first part, feature extraction. What we use, I'm going to also make a pause and tell you, I'm not sharing what's the best right now, right? This is more like what have worked for me and what can you apply for your projects if you have or if you are interested in doing these kind of things, right? This is the feature extractions, and what we are using is the mel frequency cepstral coefficient. And these features basically try to mimic or to reproduce what a human ear is capable of doing. were introduced a long time ago in the 80s. But nowadays, we are still using them to speech recognition, environmental sound classification, but also for songs. When you want to recognize a particular song, it's also employed for that. And fortunately, we have this already implemented in MATLAB in the audio toolbox or in Python with the Librosa package. So, not to be too technical, you have the signal, and what the male frequency substral coefficient uh, do or does is break this signal in frames, overlapping frames, and then you apply this Fourier transform, right? And as you might know, it's to get the energy of the signal, the spectrum of the signal, and then you apply this filter bank, the male frequency, what it's called male filter bank. We are using, or this one uses the male scale. Male comes from the word melody because it simulates more the what the human hearing does. Especially, well, there's one really nice example in which you have some noise that it's between 300 and 400 hertz, and another one that it's or whatever, right, 300 and 400 hertz, and then you have some other noise that it's between 900 hertz and 1000 hertz, and you can see the difference of sorry you can hear the difference we or the high noise, right, like even that the difference it's only 100 hertz, or identify this difference in a better way when you have high frequency noises. So the male frequency scale tries to simulate that. And also you have this application of the logarithmic scale that it does more or less the same. Discrete cosine transform, which basically tries to by having all these overlapping, you have some how can I explain? By having you have sorry, all this overlapping, you have some correlations, and you want to there correlate by applying this discrete cosine transform. But that's a very short explanation. I have at the end a couple of sources that you can use that I think are really good to understand all these feature extraction techniques. So that's what we apply. And what we did was to each one of these samples get 13 male frequencies. And how did that? Because we have a lot of samples and we want to do it kind of quick, right? In the computer, it's going to take a lot. So I'm going to share what it works for me too, the high throughput computing. And this is it's a use of distributed computing resources for the application or to use it as a computing power to do things faster. So in short, I'm going to say high throughput resource to complete your analysis in a shorter time, right? And the one that I use is HT Condor, which is an open source. Something that I recommend, especially if you don't have access to, or let's say your institution, you don't have access to all these huge clusters, there is this Open Science Grid that it's a nationally funded consortium in which you can make use of all these resources. And I think it's open for anyone for any institution in the country. That's what we use. Also, I'm not intending to hardcore lesson of how to make your programs, but to show you that it's not hard to do it. So we basically need 3 of these files. And the first file, it's the code that we, want to repeat the task. In this case, the task that I want to repeat, it's to, for each one of these samples, take the male frequency coefficient. So we have here, the extraction happens here, you have the code. Then you have this other code in which you are calling the original, the feature extraction code. And basically you are telling the computer, this is the amount of memory that we are going to use, save the data in this place, things like that. And then you have one more code that runs this string code several times. And this is when I'm going to say the magic happened, right? Instead of doing for loops and waiting for a long time, you just make your submission file and your DAG file, what it's called, that DAG file, and you can, ask the computer to do thousands of these jobs, and they finish really quick. So this is what we use for our analysis. For example, in this file, basically what you are stating that have several jobs, job 1, 2, 3. You have which submission file you are calling, and remember the submission file basically calls the original file plus some parameters. And here you are asking or including the parameters or not the arguments, of your original code. What is the channel that we are, what is the sensor that we are analyzing? The GPS time, this is the time at which we want to start our analysis, and the duration. The next step. So now we have many of these samples, and we have for each one 13 to apply some dimensionality reduction, right? Because this is to easier visualize what's going on. We have 13, in this case, 13 dimensions, 13 coefficients. So what we want is something that, as humans, we can understand better. So what we applied was this T-distributed stochastic neighbor embedding. And you can see we have a two-dimension plot in which we see different groups. Then, well, the first thing that we did was, once we find all these groups visually, we can apply spectral clustering that also makes all these groups automated way. What we found is all this list of different, what we call peak down and peak down. Actually, it's something that it's present in the microphone, but it's more electrical than a sound itself. But we have also white noise, thunder, some kind of chirping, doors opening or actually closing really hard, vehicles passing by. But what is nice of this plot is that you can see the groups. Right now that you can see it, you want to do some automated version of this grouping. That's when we apply the spectral clustering. And for this analysis, we use only triggers with signal to noise ratio higher than 100. Why? Because this is what we expect, or these triggers are those that we expect to have the highest effect, right? Because we are assuming that as the noise is louder, the ground motion will be higher, and that will produce more scattering, and therefore we will have a higher effect on the gravitational wave channel. So in total, we have 665 of observation for the LIGO Livingston Observatory. So what did we see in the gravitational wave detector? These are the three noises that have the highest effect in the gravitational wave detector. Thunderstorms, that's something that we were expecting. And this is an spectrogram. Actually, we call them omega scans, and they use the Q transform instead of the Fourier transform, but these are time frequency maps basically. And what I'm gonna say is that blue it's good, blue it's not a lot of noise, yellow it's noise. Right? And we have on the X, we have the time, and on the y-axis the frequency. So at a given frequency, at a given time, what is the noise in the sensor and the gravitational wave channel. All the top row is the microphone channel. The bottom row it's effect in the gravitational wave channel. So let's take a look to all of these. Thunderstorm, we expected something like that, and you can see that have an effect in the gravitational wave channel. Vehicles passing by, these probably this one we cannot mitigate them. This one depending on the vehicle, but maybe we can be more careful of the vehicles going around the facilities, but you can see also that you have some noise. And this is something interesting. Closing doors are very loud, and you can see the effect in the gravitational wave channel. By the way, there are logbooks, so I'm not sharing something that it was not known, but I'm sharing some data, with some kind of value, because we know that these closing doors might produce noise in the gravitational wave channel, but here I'm saying how much, right? And as you can see, a single door closing very hard, you can have some noise. I'm not saying, but it can happen. So it's important to take a look. So that's how we, or the way that we find the origin of all these noises, of the scattering, and maybe we can mitigate some of them. And the last thing that we did was the supervised learning. That is the classification of all these noises. So what we did was to use the data that we already find by grouping, and now we use them as a training set. Unfortunately, in MATLAB offers a very convenient tool that compares the performance of all these classifiers. In this case, we use decision trees. We also use support vector machine and k-nearest neighbors. That it's something is one that my favorite. It's the easiest to understand, and it's also a kind of quick to train. And as you can see, in our case, the KNN algorithm was the one with the highest performance. And you can see all these groups that in a previous slide I showed. We have the vehicles, thunderstorm especially, and then we can analyze or anticipate. So once we choose this classifier, usually in LIGO we use a lot of Python scripts. We can apply all of these things into Python, and then we can make an automated tool. Here we haven't implemented. The plan is that we use them for what we call data quality report. So the data quality report are these reports to validate event candidates, and the idea is that we make all these reports more automated as the years pass by, right? So, as a summary for this presentation, we have these gravitational wave detectors that are very sensitive, and therefore it's very common that we have some effect by noises, in this case acoustic noise. We employ the microphones, machine learning techniques, and I'm going to call it HT Condor, that it's this high throughput computing framework to find the origin of the noise. We implement central coefficients to obtain all these features from microphone recordings, and the noise produced by all this acoustic noise, especially from thunderstorms and vehicles pass by, they have an effect in the gravitational wave channel. And this tool complement the data quality reports for the gravitational wave event candidates. And the last slide that I have, it's about all these resources. So in case you are interested in the male frequency cepstral coefficients, by the way, the word cepstral, you might haven't heard it before, and it comes from a spectral, but with spec backwards, because you apply basically, this is a spectrum of a spectrum. So it's not in the time domain, neither the frequency domain, and therefore they came with this new word. And these are, as an introductory resources, are really good. In the computational resources, we have these two packages, Librosa, that it's very good for the feature extraction techniques, and scikit-learn for the classification, the grouping, clustering and classification, but also for dimensionality reduction. But also for MATLAB, we have these two toolboxes, the audio and the machine learning toolboxes. And for the high throughput computing, I recommend this Open Science Grid. And I finished early, but that's all I have for now. Thank you.
Thank you.